Okay. So last time I described uh, the s- the strategy to prove this general Liouville type theorem for conformally invariant equation. So, and I think uh, I it, I think oh I think maybe so I will do the following. So since the proof involves some um, so since the proof is a moving spheres procedure and plus uh, to prove this solution near infinity uh, have appropriate behavior. So 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 maybe I will separate the presentation. So I will first presenting the procedure. So I will give a proof of this classical result of Caffarelli, Gidas, and Sprague. Use the strategy, use the moving sphere uh, method. And then I will address the isolated singularity issue like removability of isolated singularities for super solutions of this more general equation and and uh, and the ingredients needed for the more general. Yeah, I separate them. Okay. Okay. So let me. Okay. So then I will just. I think it's easier. Maybe this way is easier. So let's look at this theorem of Caffarelli, Gidas, and Sprague. So so that's the theorem. Okay. So let's prove this. So this is the Kelvin transformation. So this y is in Rn minus this. So this is this corresponds to that conformal Mobius transformation x. This is lambda. So this is about, so there's a phi x lambda. It maps y to x plus lambda square, y minus x, y minus x squared. So it keeps the boundary fixed and maps inside out and outside in. And this ux lambda, this is the u with respect to this conformal transformation. So I just denote it by that. So we know that by the invariance, conformal invariance, we know that minus we know that ux lambda is also a solution because this is a solution, this equation is invariant. So we know that minus Laplacian ux lambda is also equal to the same. So we know this. So lemma, okay, I said step 1. So the state, so this is about, this is x, this is lambda. I'm writing outside. So this is outside the ball. So we have this. So this is the same as writing inside. So last time I wrote inside. This is equivalent to, you just on both sides, you do a Kelvin transformation. This is equivalent to u of y less or equal than u x lambda of y for every y minus x less or equal than lambda, bigger than 0. So inside. So this is outside. They are the same. So after you just take this expression, you make a Kelvin transformation, they are just the same. So you can write whichever way you feel more comfortable. So when you work with this version, the singularity is at infinity. So when you work with this version, the singularity is at x. So namely, so here inside this function, it's a solution, but it's a solution in a punctured ball. U is a solution in the ball. So when you write like this, they are all solutions outside, but but this ux lambda is very good at infinity. Yeah, it's a quote unquote C2 at infinity. The U has a singularity there. So it's just the same, whichever way you feel comfortable. So, okay. So to prove that, so let's prove this. Okay, so prove this, proof. So without loss of generality, we may assume x equal to 0. Okay, because this equation, everything is translation invariant. So when you say this, you just work with the translation by x. So for your new function, it's at 0. So you just need to prove this. Yeah. So we use shorter notation. So now we write u x is 0 lambda. We just write it as u lambda for simplicity. Okay. And the reflecting ball, yeah, okay, yeah. Okay. So we write our function as u r theta in polar coordinates. So this is in polar coordinates. So namely, we have a 0 here. We have a r and theta. We have r and theta, r and theta. This is theta. Or theta in Sn minus 1, boundary of the ball. Yeah, theta. R and theta. So you just take a ray and you multiply by r to the n minus 2 over 2. You take derivative. You will see this is positive for small r. There exists r0 positive such that this expression is positive for all r less than r0 and for all theta belongs to Sn minus 1. The reason is, you see, this is this derivative. So this is Lipschitz. So when you take this differentiation, the expression you get when you take derivative, when you hit r, you get a term n minus 2 over 2, r to the n minus 2 over 2 minus 1. Okay? And then you times u. Plus, then this does not move, and you take dr of u, r theta. So this is bounded because we assume that u is locally Lipschitz. So this is locally bounded. And u is positive. It has a positive lower bound, of course, because it's continuous. A lower bound it's positive, so there's a lower bound. So now the r, this term is r to this power minus 1. So this term is that. So this has one more r minus 1, which is huge when this r is small. So therefore, when r is small, this term dominates, and therefore it's positive. Okay. So what we showed here is you have a 0. Let's take this theta. Then you go a distance r0. So this is r0 theta. Okay, this is r0. So theta is fixed. This r0. So we have a function in R. This function is positive in this interval from 0 to here. Okay, this positivity, when you that tell you this function is non-decreasing. Okay, increasing actually, strictly increasing. So this translate to, you just write down, this is a one variable function. You have this, you just rewrite it, you will see that this is the same as, this is the same as. So when I say the derivative, the strictly increasing, and what I'm writing here is the same, right? Okay, maybe. So I will just write, it is actually the same. So, okay. So it is the same as u lambda y will be less than u of y for all 0 less than lambda less than y and less than r0. Okay. So this is the same. So namely, this moving sphere can get started in this region. So in this region. So this is true. But yeah, okay. So anyway, so this is true. So you have this. So if I draw, this means 0, I draw a lambda here. Okay, for any lambda, this is your given r0. R0. So in this annular region, you have u lambda less than u. So what you want to prove is actually outside also you have this order. Oh, okay. So you get here up to r0. This is just following from that. Okay, so now since u is superharmonic, because minus Laplacian u is equal to n minus 2, u n plus 2 n minus 2 is actually positive. So this is superharmonic. So therefore, at infinity, so because it's superharmonic, so u is very good, has very good behavior at infinity. You can use maximum principle. So then, so we can use we use maximum principle to obtain u of y. This is one function. The other function is the minimum of u on the boundary of this BR0 ball, which is a positive number. We assume u is positive. Then R0 n minus 2, y 2 minus n. So for all y greater or equal than R0. So what we are doing is We are doing it, we take this ball of radius r0 and we look at outside. Okay, we look at outside. So the right-hand side is harmonic. This is harmonic. Laplacian is equal to 0. This is harmonic. And this one is superharmonic outside. And they coincide, they are the same on the boundary. Okay? They are the same on the boundary. One is smaller than that on the boundary. This inequality holds on the boundary. Because on the boundary, this is equal to 1. So u is bigger than the minimum. So on the boundary, you have that. And at infinity, right-hand side goes to 0. Well, u of y is positive. So lim inf of u of y greater or equal than 0. So in this case, the maximum principle can be applied. Even though the maximum principle is for bounded domain, this allows you to use some elementary consideration to work in a very large ball minus this little ball. Okay, so you apply maximums at infinity, you have order. So this just comes from a standard maximum principle. So then so now, so actually in the remaining, actually the proof we use is we only use this fact. So here we get goes in positive. So this is important in the rest of the argument. So we actually you will see only use this. In the general case, in the general fully nonlinear, more general case, this is what you need, and this we don't really have. If it is superharmonic, you have, but in general, for more general case, you have to prove that you have to get this property under some positivity of the Hessian and so on. Okay, so here you just have it very easily from the standard maximum principle for harmonic functions. So then after this, let's let lambda 0 to be equal to R0 minimum u. So you just pick a number. So actually for this lambda 0 sufficiently small relative to the smallness is relative to this R0. So we simply just write down explicitly. If you just take this, certainly this is less than that. Okay, you take that. Then for every 0 less than lambda 0, and for y bigger than R0, we have u lambda of y equal to lambda divided by y n minus 2 u lambda square y over y square. So it's going to be less or equal than lambda 0 divided by this, because lambda is less than lambda 0. And this y is bigger than this, so the inside is actually smaller than R0. So therefore, you can write it as maximum of U be R0 bar. Okay. So this, okay, and of course we have a super harmonic function. So the maximum no, that's not true. Yeah. Well, I'm using this lambda zero. I'm using now I use maximum U. Maximum U should be, I use this property now. I use this property. So I will see you raise to n minus 2 power lambda 0, multiply that will be bounded by y to the n minus 2 times R0 n minus 2 minimum boundary BR0 and the U. I have this. I'm using this. But you know that this is for y bigger than R0. On the other hand, we know also U is bigger than this. So we know this. U is bigger than this same expression. This is the same expression. So this is then less or equal than U of y, because for y greater or equal than R0, we have it from here. We have here. We use this. So, namely, with the choice of that lambda 0, with the choice we have U lambda y is less than U of y for all y bigger than lambda. This is what we showed. We first say, I should first say the above I have bigger than R0, because here we have R0, okay? However, we already showed here the same inequality for y less than R0 and bigger than lambda. You put together. You see, previously we did this inequality for y in this annulus. Now we are doing for outside. So combined with the earlier estimate, combined with the earlier estimates for y bigger than lambda and less than R0, we have U lambda y less or equal to U of y for all y bigger than lambda, because this part plus that part. So this is, so step 1 is completed. Okay. So if you think of our more general equation, so what, and compared to this equation, so for this equation, we mainly used this to obtain this property. Okay. Once you have this property, all the rest will be some comparison principle. So we didn't use comparison principle. That's it. We just use this. Okay. So namely, for the general case, if you can deliver this property, then you are okay. So this is a property for a solution near a isolated singularity. The isolated singularity now is at infinity, but of course, when you make a Kelvin transformation, you can put the isolated singularity at 0. So for this step, you need to have appropriate property for isolated singularity solution. And of course, you use the fact that your equation is conformally invariant. So for our general equation, we only look at conformally invariant equation. Okay, so okay, so now we go to the another step. Step 2, let's say. Step 2. So if the lambda bar of after step 1, we can define lambda bar now. Okay. So we can define for x in Rn, we can define lambda bar of x to be sup So this means the moving plane procedure, the moving sphere procedure. So the radius of the sphere, you go to the maximum. Okay. So we know now this number is bigger than 0, but can be either a positive number or infinity. So step 2 is if this number is finite for some x in Rn, then u x lambda bar x so will be identically equal to u in B lambda bar of x and centered at x minus x. No, actually, it's also, once you have inside and outside, it's also okay. So you actually have Rn minus x. Yeah. So the picture is you have an x here. You go to the maximum lambda bar x for this property. So you see for small lambda, step 1 says for small lambda, you have this property. So the Kelvin transformation is less lying below your function u, outside the ball of radius lambda. So lambda bar is the maximum of such lambda with this property. And then now, if it is finite, it's you actually say it's the same. The same. So to prove it's the same, to prove it's the same, you only need to show identity outside the ball. So once you prove this identity outside, the identity inside will follow immediately just from the definition. You make a Kelvin transformation for this equality, you will see the inside. So okay. So step two, you can say you just need to show this identity outside this ball. Okay, so let's prove that. So again, so without loss of generality, x equal to 0. And now we denote lambda bar is lambda bar centered at 0, and u lambda, we denote this u0 lambda as before. Okay. So let's, for simplicity, let okay. So let sigma lambda to denote no, let's now to introduce another notation. All right. Okay, good. So okay. So we'll show outside. So we'll show u lambda bar identically equal to u inside on Rn minus the ball. Yeah, we'll show that outside this ball. So we know from the definition of lambda bar, your u lambda bar is less or equal than u on here. Yeah. So the ball that you have a 0, we work with outside. This is lambda bar, we work with outside. Yeah. So outside is Rm minus this B lambda bar. We work outside. So this is from the definition, we have this. So as mentioned before, minus Laplacian u lambda bar is equal to n minus 2 u lambda bar n plus 2 over n minus 2. And in here. So this is the conformal invariance. This is the conformal invariance. So, and the original equation is this equation. So here, so this is because of this is important. This is conformal invariance. This is the original equation. Conformal invariance give you the above equation. So here, because our equation is simpler, we immediately know that, you see, right-hand side, this is smaller than that. So therefore, this is smaller than that. This tells you minus Laplacian u minus u lambda bar is actually greater or equal than 0. So you know the order. So this is greater or equal than 0. Namely, u minus u lambda bar is a superharmonic function. So this is in Rn minus b lambda bar. So if u minus u lambda bar identical equal to 0 in Rn minus b lambda bar, we are done. We stop. We stop. Then step 2 is finished. Otherwise, so by the strong maximum principle, u minus u lambda bar should be positive in the interior. Okay, because once non-negative function achieves 0, so now we actually have a superharmonic function, so it will be identically equal to 0. Then you are done. So you have this, and then by the Hopf lemma, so you have a superharmonic, positive superharmonic function. U minus u lambda is equal on the surface. This is equal to 0. And outside is positive. Okay, so therefore, the Hopf lemma tell you that, and this is superharmonic. So this derivative must be radial derivative. I didn't draw it properly. This is derivative. So d(r) u minus u lambda bar should be positive on here. Should be positive on here. If it's positive, so this is a C2 function. This is a compact set. It has to be bigger than some fixed constant. Then by continuity, nearby is also bigger than some constant. So I will just simply write it as bigger than a positive constant, positive. And for some, so you can say there exists R bigger than lambda bar. So for lambda, I can even make this lambda move around. For lambda bar less than lambda less than R, and for R bigger than lambda less than r. Okay, so because when you freeze lambda equal lambda bar on the boundary of the sphere, you have positivity, then by the continuity of everything. So our picture is lambda, and you put out a small layer. This is R. So inside here, lambda allowed to be bigger than lambda bar a little bit, you still have positivity. So this means, consequently, okay, since u minus u lambda equal to 0 on boundary B lambda. So we know that u of y minus u lambda of y will be bigger than 0 for lambda bar less than lambda less than r, and for y bigger than lambda and less or equal to r. You have this property because the derivative is positive in this range. Now let's take C equal to the minimum boundary BR and u minus u lambda bar. So it is positive because a positive continuous function, the minimum is positive. Okay. And then by the superharmonicity, okay. So we know that u of y minus u lambda of y will be bigger than lambda bar, okay, will be bigger than C R n minus 2 y n minus 2 for all y bigger than r. The same trick as before. We compare to harmonic function, superharmonic maximum principle, you have this. Okay. Therefore, so here superharmonicity of u minus u lambda bar is used, this used come from our equation. Okay, so now this tells you u of y minus u lambda of y will be bigger than C R n minus 2 over this minus u lambda of y minus u lambda bar of y. Okay, because here is lambda, so you have to use this estimate, so you have an extra. Then, by the uniform continuity of u, on this ball. So there exists 0 less than epsilon, very, very small, such that for all lambda bigger than lambda bar, less than lambda bar plus epsilon, we have So what I'm saying is, you see, when lambda and lambda bar are very, very close, if lambda equal to lambda bar, it's just identically equal to 0. So everything here is infinite range, y over y, because y is large, y over y squared is small, so everything stays in a bounded domain. So therefore, you have uniform continuity, so this is true. Okay. With this, you see, then it follows from the above that u of y minus u lambda of y will be bigger than 0 for all lambda bar less than lambda bar plus epsilon, and for all y bigger than r. Because this is, you have this. Now, this is exactly that. This is control is less than that. So, and so, right. So you will see, you will, you put it there, you will see, you just use this here, you will see this positive. You just put the original, this is u lambda, this is that, this is less than this. Yeah, CR over 2. This is not that. This is differ by multiply this y. So I think here lambda, probably I should write n minus 2 here. So then I will match. So then this will possible. Okay. Okay. So this means, so from here, and previously, this y less than r. We have somewhere for less than r. You see in this for less than r to here. So from here, you put these two together, combine the earlier one, you have u of y minus u lambda of y is bigger, greater, equal than 0 for all lambda bar less than lambda bar plus epsilon for all y actually bigger than lambda, because the part in between lambda and r is being handled by early estimate. So this means this violating the definition of lambda bar. Because lambda bar is supposed to be the largest radius the moving sphere procedure reaches. So, but now for lambda bigger than lambda bar, less than lambda bar plus epsilon, this moving sphere procedure still works. So lambda bar it violates the definition. Yeah, you actually. So step 2 is finished. So once step 2 is finished, the rest just follows from uh, from appropriate calculus lemma. So I will, as I will explain. So you can say, I can say step 3. Let's say either uh, either lambda bar of x identically equal to infinity for all x in Rn, or lambda bar of x finite for all x in Rn. Okay. So proof of step 3. So if lambda bar x bar is equal to infinity for some x bar in Rn. If this never happens, then we have this is finite, okay? So if there is one point equal to infinity, we will show lambda bar will be infinity everywhere. Okay. So if this is true, so then by the definition, we know that u of y will be bigger than the Kelvin with the reflection lambda y. This is true for all y minus x bar bigger than lambda and for all lambda positive. Because for every lambda, you have this moving spheres procedure can reach there. So you have this order. Okay. So now, what does that mean? So this means, so let's write it what this means. This is just lambda over y minus x bar. This is the definition. Okay. So now I will multiply this, multiplying that. And then I multiply by n minus 2 u of y. And then you take limit inf as y goes to infinity. You will see that it will be bigger than right-hand side. You will see this is equal to right-hand limit exists. So you get this. Because when you hit by y to the right-hand side, you have a limit. Now send lambda to infinity, because this is true for every lambda. We have lim inf this equal to infinity. So we have limit y goes to infinity, y and minus 2 u of y should be infinity. So you will see that this rule out the possibility that lambda bar x finite anywhere. So I can say it's like this. On the other hand, if lambda bar x less than infinity for some x, then by step 2, we have an identity. We have u of u x bar, u of x. We have u of x, lambda bar of xy will be identically equal to u of y for all y minus x bigger than lambda bar of x. But you write this out, you will see this is the definition is like this. So now if you look at this expression, you multiplying the same argument, multiplying the above by y to the n minus 2 and send y to infinity. That will give you, on the left-hand side, you will see you multiply that. The left-hand side will give you lambda bar of x n minus 2 u of x, while the right-hand side will be limit y to the n minus 2 u of y as y goes to infinity, and we said this is infinity contradiction. So lambda bar of x equal to infinity for all x in Rn. So if one point infinity or infinity. So you have proved this situation. So the fact is lambda bar of x identically equal to infinity will tell you, implies for all x in Rn, this will tell you this u is actually a constant, implies u x lambda y identically equal to u of y for all y and for all x and for all lambda positive. So this implies this fact alone will imply u is constant. So this is a calculus lemma. This is a calculus lemma. This is a calculus lemma. In fact, we already showed it. So last time the proof can be like this. You take anything like this. So you take a y, you take here y star, the symmetric point, and then you put a x like this. This radius is x. So you have symmetry. You know one side is less than the other. Then so in this case, you know that u x u x bar y should be bigger than u of y for any y belongs to here. So if I fix y and let x goes like this, now fix y. So then I have this order. So now I send x to x equal to x1, 0, 0 to infinity. I go like this. So then that will tell you, leads to u y star will be greater or equal than u of y. But these 2 points are chosen arbitrarily. And then I take the frame and so on. So this means u is constant. That's the same proof. Yeah. So this is a proof. So this will lead to that's constant, but constant is not a solution. So constant is not a solution. This cannot satisfy the equation because constant makes this zero, but this is positive. So it's not a solution. So that's out. So now we only need to show, now we know that lambda bar of x is finite. For we have proof that for all x in Rn. Okay, so this means ux lambda bar x for every x in Rn. This one is identically equal to u of y for any y in Rn minus x. So this lambda bar of x is positive. So here, there's another calculus lemma. Whenever a function u, okay, you take a function u, any continuous function with this property. With this property, this tells you your u of y must be, and your u is positive actually. So, and you, let's say, notice u is also positive. So otherwise, this, so okay, you have a 1 plus b squared x minus x bar n minus 2 over 2. A, b positive, x bar in Rm. So this is a calculus lemma. Okay. So now you have this form. So we know that we, we write it. You think of this way. We write u of y equal to a over b n minus 2 over 2, and then b over 1 plus b squared x minus x bar squared n minus 2 over 2. I call this u hat y. So I know that this u hat y satisfies that equation. I know that. So now the u is a constant multiple of that. So you look at it, this exponent is not 1. So in order for constant multiple of a solution to be still a solution, this constant has to be equal to 1. So you prove your theorem. So u of y is identically equal to a over 1 plus a squared. Yeah. So this proof is very robust. So it uses for superharmonic function, some isolated singularity behavior for superharmonic function. So therefore, if and the conformal invariance of the equation. So if for our very general conformal invariance equation, if we can deliver appropriate singularity behavior, like we've described before, I mean, those like a removability of super solution for isolated singularities, and if we have some strong maximum principle for one C2 and for one lower semi-continuous, okay, then you see along the way we used some strong maximum principle. Yeah. And so if we have all those ingredients under control, we are able to prove Liouville type theorem for conformally invariant equations. So therefore, next time I will be addressing uh, a couple of the needed uh, uh, properties for uh, isolated singularity behavior of supersolutions and so on, those properties. And then once you have that, this proof will just can be implemented the same way. Okay. And any questions?
Any questions? Professor, sorry if my question is a little imprecise, but we also talked about a lively type theorem yesterday, isn't it? Your proofs. So there we talked about this lambda star, the distinguished point is being in the gamma closure or not.
Can you speak more slowly?
So yesterday we had a similar lively type theorem.
But
So
wait, yeah.
in yesterday's talk.
In this talk?
In yesterday's talk, the previous talk in talk.
Yesterday's talk. Okay.
So you also had something, the distinguished point lambda star to be in gamma closure or not. Depending on that, we are able to make a conclusion similar to the solution expression like this. We had a by 1 plus b square. So
right.
that point being in gamma closure or not, similar to that, is it reflected in today's proof of Caffarelli somewhere, being in the construction?
Yes. For example, very good. So for example, we wrote that so our first step one uses three properties. Step one is the beginning, the moving sphere, procedure can get started. So it only uses this property. One is 0 less than u, and belongs to C01 log Rm. Okay? And also used lim inf y to the n minus 2 u of y goes to infinity is positive. Okay. So this one, we have it in general. So just this property. So this property, is at infinity. Okay. So if making a conformal transformation, or you can just say that. So you can just say that. Okay. So this property, this means this equation. So we use the fact that this equation is satisfied in, say, y bigger than a constant. Okay. So we get this. Okay. So this means this PDE near isolated singularity at infinity have this behavior. So you have this. Okay. So then what I'm saying is if this if lambda of AU for this one, if this lambda of AU belongs to gamma bar, and this gamma bar has enough positivity, so this is in y bigger than 1. Okay. So this we can show, imply, okay, we can prove, can show this property holds. So, which means if you have this property, then the first one can get started. And of course, plus, yes, you can get started. So also, this is necessary and sufficient for this. So this positivity is necessary and sufficient in the sense that whenever this gamma bar is violated, namely, so actually this property, this positivity property is optimal in the sense that if lambda star belongs to gamma bar, okay, then exist U positive and smooth inf limit of that is there is not positive. Limit is 0. Lim inf y n minus 2 u of y is actually 0. So namely, so this positivity is necessary also. So this enters into the proof. For example, if gamma belongs to gamma 1, okay, then this property holds, of course. So in this case, so this is better than this. Yeah. In this case, lambda AU belongs to gamma in gamma 1 implies Laplacian U is less or equal than 0. So then today's proof for this step, for this part, works. Okay. So today we use this superharmonicity. But in general, you don't need this much positivity. So this positivity is enough. Yeah.
And just one more clarification. So in yesterday's theorem 2, you also made a similar conclusion for the expression of the solution U, but you had the two constants A and B. What stopped us from concluding there? It has to be equal to B.
That's right. Very good. Very good. So you see, so very good. So we reached U of x must be equal to A 1 plus B square x minus x bar square n minus 2 over 2. Okay? So the fact, so you see that, so this is the fact is for such this AU is actually equal to, let me write down the number. I think this is equal to 2b squared a minus 2 identity. This is identity matrix. Okay? So this is a fact. So now there, our equation of U satisfy f of lambda AU equal to 1. So which means f of 2b squared a minus 2 multiply this vector E is 1, 1, 1 is equal to that. Okay? So however, if we know that if you put t here, E, for t positive, d dt is equal to fi lambda I te and then times t. So this is actually positive. So that means there is only one, there can only be one number. So this means for there can be only one number C bar E equal to 1. So this property tells you they cannot be more than 1. Okay? If there is a 1, they can only be 1. Okay? If there is a 1. So this tells you, so if there is a solution to that, there's 1. But now you are saying this one, there's a, so therefore 2b squared a minus 2 has to be C bar. So A and B will be related. You can only have one relation. Okay, the relation A is not equal to B. A is a multiple. Is a multiple times. It's a constant times A. Okay, this constant determined by your F. There's only one constant which can make it work because your F is strictly increasing along this ray. Yeah, this is E.
Thank you very much, Professor. Thank you.
Yes.